Okay, the video part 2 for arc length and surfaces of revolution. So in the last video, we talked about the motivation behind the arc length formula, the integral that gives you the arc length of a nice curve. So now we're going to take this curve and rotate it about the x-axis, and we're going to consider the surface area. And I've drawn a little representative frustum. Remember, I've thrown this word out there a couple times. A frustum is a cone, a right circular cone that has been sort of spread out, right? So if we look at this guy here, remember last time we looked at these little line segments and we just found the straight line approximations by gathering all those little lines. Okay, so the surface area of a frustum is 2 pi, well, and if you know that if I'm talking about a regular cylinder here, the surface area is just 2 pi r, right? And we can think of unfolding this, right? We unfold this little guy, and it is 2 pi r here, and what we call the height, I guess I am going to call it, what do I call it here? L, I guess it's an L. So this guy here, the surface area is 2 pi r squared L, but r here is the average of the two. We take the short radius right here, and we average it with the long radius, right? We find their average right in the middle. And so the radius of the frustum, in our case, is going to be d sub I, and I'm going to say right in here we have a little d sub I, and we're going to evaluate the function at f. It's going to put us right in the middle. We do know that f of d of I exists. I should have a parentheses of f there. We do know it exists by the intermediate value theorem. Remember the intermediate value theorem? If we have a continuous function on a interval from a to b, and if it's continuous, then all these y values, any y value in between, we always can find at least one c that will get there, right? That's the intermediate value theorem. So we do know that f of d sub I is defined. It's going to be there. And so I'm going to sum up all those little representative frustums. And we start at the top here. And so 2 pi r squared, 2 pi f of d sub I squared. That's the radius squared. And here's our L, which we derived last time, right? This is 1 plus the square root of 1 plus delta y over delta x squared. Remember that we did some fancy algebra. This is just the distance formula with some algebra done to it. By the mean value theorem and the use of Rolle's theorem, we were able to say, you know what, delta y, delta x at each of these places is just f prime. So here we can approximate the surface area with n representative frustums. About this guy, I do like that word. And of course, the true surface area we will obtain if we let n go to infinity, right? This is all these let n go to infinity. I'm just saying the same thing over and over, and voila! Just as we've been taking these summations, these are called Riemann sums. Just as we're taking these Riemann sums, and we have found, if you watched, and I know a couple of you did, watched my 4 videos on the definite integral and how that relates to area. I didn't quite prove it, but I hopefully gave you enough intuition as to why that is why we can accumulate these little things and turn them into an integral. So last time this is the formula for arc length, remember? And I think I used a big S. I should have used a little s because we use a big S for the surface area. Okay, if these things look like complicated expressions to you, they are. And they're not very easily dealt with. And so I'm going to give you 2 examples, but I went to GeoGebra to do them. So look at the first one there, 3/2 times x raised to the 2/3. And going to quickly do something here. And it's really not really that fancy of a graph, by the way. It just kind of looks like a square root, right? But well, it just kind of does something like this, right? And goes up, and so we're going to take from 1 to 8. This guy right here, we're going to rotate this around the x-axis. It's going to look something like that, and we're going to find the surface area of it. So I'm just going to set up the integral. The integral for the length of an arc is given by the integral from A to B of the square root of 1 plus f prime of x squared in dx. And so what I'll do for this one is I'm just going to find f prime of x. F of x is 3/2 times x raised to the 2/3, so f prime of x is just x to the minus 1/3, and we're going to square that. So f prime of x squared is x raised to the minus 2/3. So I'm just going to enter this integral. I'm going to enter the integral from 1 to 8 of the square root of 1 plus x raised to the minus 2/3 dx. I go plug it into my GeoGebra. Remember that GeoGebra will do integrals, and all you have to do is the function. So it's easiest, in my opinion, to enter this as a function. Say f prime of x colon equal this thing, this whole guy. And so then when you get to your integral, all you have to write is integral f of x from 1 to 8. You hit enter, and you know what pops out? Something really nice. 5 square roots of 5 minus 2 square roots of 2. So that's an interesting one, huh? Okay, look at the next one. This one's even more interesting. And this is a nasty bugger if you try to do the integral by yourself. So you are going to use either Wolfram Alpha, Mathematica, or GeoGebra. Actually, I tried this one on GeoGebra and it crapped out on me. So I went to wolframalpha.com and it worked fine. Okay? Find the area of the surface of revolution generated by resolving the function sine of x plus 2 on the interval 0 to 2 pi about the x-axis. So you see my drawing there, and you can imagine what that will look like. I don't think I should even try to draw it because you guys have seen me draw, and goodness gracious. Well, I don't want to do it. I'm scared. Something like that, huh? Right? So, yeah, that's not too bad. That's pretty good, actually. This one will be dotted. Yeah? Something like that? No. Yeah, heck with it. Okay, so f prime of x. The derivative of the sine of x plus 2 is just the cosine of x. The second derivative is the minus sine of x. And so we are going to do, should I put the whole thing on here again? The area for the formula for the surface area is 2 pi times f of x squared times the square root of 1 plus f prime of x squared dx from A to B. So I just entered as a well, I'll do 2 pi times the integral from 0 to 2 pi of sine of x plus 2 squared times the square root of 1 plus sine squared x dx. Right, it is minus sine, I do know, but we're squaring it, so I'm just going to get rid of that negative. Okay, so I entered this guy as a function into Wolfram alpha and said evaluate it, and it gave me a question mark. And then I entered all this into GeoGebra, or into Wolfram alpha. I just said, find the integral of, and then I just wrote this out. I put a parentheses here, and I put everything in there, this part, and I put a dx at the end, and I wrote the words from 0 to 2 pi, and then I put another parentheses around the whole thing, and I multiplied it by 2 pi, and approximately 218 came out. 218 square units. And you notice that's not a nice exact answer like this one was, because this is a really, really nasty integral, and it's going to evaluate it numerically. So we had not evaluated things numerically, but all you really do is you just don't let the number of rectangles go to infinity. You stop at some big number, right? The computers can just crank these things out, so maybe we want to know, hey, what is the area if we do 200 frustums in here, or 3,000 frustums, or even 1,000,000, right? The computer can do that pretty quickly, and that's what it did in this case. It evaluated numerically. There's something called the trapezoidal rule. You can put little trapezoids in here, and there's something called Simpson's rule. You guys that are going to be engineers, I'm sure you'll study it. Okay? That's it. We're done. I'm going to give you some problems to work. I'm going to let you choose which problems you want to work on. Make sure you kind of understand the process, and you can enter a couple of them, try a couple of them, and then just look at whatever problems are most interesting to you. Get a hold of me if you have any questions. I've been doing that for all the videos lately.